Okay, so analyze the mono truss. I would imagine that this would hold up a roof. Notice that it slopes in only one direction. So first you notice all the dimensions in the geometry on here. Get the dimensions down. 4 sections along the bottom, 3.75 feet each. It's 8 feet tall at its high end. I've got 2 reactions at A and 1 reaction at F. And notice I've got 300-pound loads at B, C, and D, and there's a 200-pound, maybe a wind load at C. So I could consider the 300-pound loads to be snow loads, for example, and maybe the 200-pound horizontal load would be a wind load. But whatever the case, I want to analyze this using the method of joints. For the method of joints, at each joint, the sum of the forces in the x direction has to be 0, and the sum of the forces in the y direction has to be 0. Now, the method of joints is quite cumbersome. At each joint that you're analyzing, you can't have more than 2 unknowns, and so I can't just start at any joint when I use the method of joints. For example, I cannot start at joint D because I've got 1, 2, 3, 4 bars that feed into joint D. It's too many unknowns. So I have to start at a joint at which there are only 2 unknowns. So in just a minute, I'm going to calculate the external reactions, A sub x and A sub y and F sub y. And once I do that, then I'll be able to start my analysis at joint A. Notice these angles that I have here. Alpha is this angle down here. This is angle beta, gamma, delta, and then these thetas. Those are all the same. Create some special triangles based on those. So get a good look at the geometry of this, and I'm going to replace this with another slide. Okay, so I'm going to get my trigonometric relationships from this slide. Notice the alpha, theta, beta, gamma, delta, all those angles that I have. So I'm going to use these triangles when I go to look for sines and cosines. Okay, so calculating the external reaction, sum of the forces in the x direction is 0. I get A sub x is 200 pounds to the left. The sum of the moments about point A is 0. I get F sub y 503 1/3 pounds. Okay, you know where I'm getting these numbers? Okay, and then the sum of the forces in the y direction is 0. So I get A sub y is 396 2/3 pounds. Okay, pause the video and go back and look at my drawing of the truss if you don't know where these numbers are coming from. So I find my 3 reactions. So let me bring back my original drawing. And I put the reactions on the figure. Those are the reactions I just found. Okay, in case you're confused as to where some of this comes from. Okay, I think the sum of the forces in the x direction and the y direction are pretty self-explanatory, but for example, the moments about A, negative 300 times 3.75. Okay, so moments about point A, the 300, that tends to want to rotate this in the clockwise direction, so it's negative. A moment arm 3.75, minus 200 times 4. So that's this horizontal wind load at C. The moment arm is 4 because here's A. The perpendicular distance between A and the line of action of 200 pounds is 4 feet. I've got it labeled here on the drawing. Minus 300 times 7.5. That must be this 300 pounds. 7.5 is from here to here. 3.75 times 2. That's the 7.5 that you see here. Minus 300 times 11.25. That'd be this load. And then the plus F sub y times 15 here. The right reaction times 3.75 times 4, that's the 15 feet. So I have all the external reactions on here. So I'm going to analyze this using the method of joints, starting off at joint A. And now here's my drawing of joint A. So the 200 pounds to 396 2/3, those are external. I have 2 bar forces, F sub AB and F sub AI. If I don't know the direction of the bar force, that is, if I don't know if it's tension or compression, I assume that it's in tension. If I get a negative, then I'll know that it's in compression. So notice that I show the F sub AB and F sub AI bar forces pointing away from point A, joint A, because I'm assuming tension. Okay, let me go back to my original drawing. Okay, you see what I have here? A, joint A sub x off to the left, A sub y going up. Bar force F sub AB, that's directed along AB. Okay, so this is the assumed tension force in bar AB. Then AI is horizontal. That's the F sub AI. With regards to the subscripts, the first subscript, at least the way that I write it, the first subscript is where the vector starts, the second subscript where it's heading. So F sub AB would be the bar force from A to B in bar AB. Okay, so for this joint, it has to be in equilibrium, so the sum of the forces in the x direction has to be 0, and the sum of the forces in the y direction has to be 0. So I'm going to write two equations based on that. And there it is. The sum of the forces in the y direction is 0. I did that part first. So F sub AB sine alpha, here's angle alpha, the sine because I would be talking about the vertical component of F sub AB, plus 396 and 2/3, that's the A sub y you see here. Sine of alpha is 8/17. How do I know that? Go back to my special triangles. Remember these? So alpha, sine opposite over hypotenuse, 8/17. Okay, so solving for F sub AB, I get negative 842.9 pounds. The negative means the bar is actually in compression, so I'm going to put the box around this answer that has a negative sign for mathematical purposes, but for practical purposes, F sub AB is 842.916, the 6 repeats, pounds. The C means it's in compression. Okay, so now the sum of the forces in the x direction. And like magic, it appears. So the sum of the forces in the x direction is 0. What have I got? F sub AB, cosine alpha, cosine because I'm talking about the horizontal component of that vector. F sub AB cosine alpha plus F sub AI. That's purely horizontal, as you can see. So I don't have to multiply by any sine or cosine. Minus 200. What's that? That's the reaction A sub x. Okay, so F sub AB, I just figured that out above, so I stick that in here. Cosine alpha, 5/17, how do I know that? Go back to my special triangles. Cosine of alpha, 15/17. So I'm solving this for F sub AI. 243.75 pounds is positive, so it's in tension. The T means tension. Okay, so that does it for joint A. Which joint should I analyze next? Okay, so here's my original drawing. Let me check this off. So I got this bar force and I got this bar force. So I'm putting little check marks there so that I know what I got so far. Okay, what should I do next? Joint B? Well, if I analyze joint B, it looks like I'll have 3 unknowns. That's too many. So perhaps maybe joint I. And now I take joint I off to the side. You see this? Joint I. Here's my original drawing. Joint I, I've got the force in IA going in the direction to the left. IH going direction to the right. Again, I'm assuming tension. IB direction going up. That's what I've got here. The F sub IA is the same as F sub AI, which I determined a moment ago. I found that to be 943.75. Okay, now, have you heard of a zero bar, sometimes called a zero member? I can tell by inspection that the sum of the forces in the y direction, having to be 0, forces F sub IB to be 0, so we would call that a zero bar or a zero member. So without doing any calculations, I can see that F sub IB is 0 pounds, or even if I do the calculation, this is all it would be. The sum of the forces in the y direction is 0, therefore F sub IB has to be 0. Okay, so that's pretty easy to tell. What about F sub IH? Okay, well, by inspection, I can find what F sub IH is. Okay, take a look at this. The sum of the forces in the x direction is 0, so F sub IH must be the same magnitude as F sub IA, so that will be 943.75 pounds in tension. Okay, so let me go back to my original drawing. So F sub IH, same thing as F sub HI. I got this bar, and I got F sub IB, that's a zero member. I got that one. So can I now analyze joint B? Okay, get a good look at joint B. I'm going to take that one out. Okay, it looks like I'll have two unknowns, F sub BH and F sub BC. So the next slide will be analysis of joint B. B as in Bravo. So does it look like I copied this correctly? Here's joint B. How does this look? Now some of this I already know, don't I? The F sub BI, I already know that. That was a zero member, wasn't it? So I can put on here 0. And then the F sub BA, do I know that? F sub BA is the same thing as F sub BA, so that's the negative 842.916 with a 6 repeats. Okay, so I know those, meaning that there's two unknowns here, F sub BC and F sub BH. Those are the two unknowns. So once again, I'm going to take the sum of the forces in the x direction, sum of the forces in the y direction. Be aware of the geometry here, the theta, the beta, and the alpha. If you're not sure where those are coming from, make sure you go back and look at the original drawing. If I didn't have that 300-pound load acting vertically, something that I might try to do is reorient the coordinate plane, make x in this direction and y in this direction. I don't think that would make this problem much easier because I've got that 300-pound load that's acting vertically anyway. But just for future reference, you do have the option of rotating the coordinate plane so that the x-axis would be parallel to this BA, BC, to the F sub BA, F sub BC vectors. But I don't think that's going to make this particular problem much easier if I do that. So for purposes of this problem, I'm going to just use x is purely horizontal and y is purely vertical. So the sum of the forces in the x direction is 0. F sub BC cosine alpha will be the horizontal component of this vector, plus F sub BH cosine beta, that would be the horizontal component of this vector, minus F sub BA sine theta, so the horizontal component of this vector. Okay, now the cosine alpha, that's 15 over 17. Okay, remember this drawing? Cosine of alpha. Plus F sub BH. I don't know that yet, so F sub BH cosine beta, what's that? Okay, I'm using this special triangle. Cosine beta, adjacent over hypotenuse. 3.75 over 4.25. Be very careful with the signs here. Minus, this second minus sign comes with the mathematical calculation I did previously. So be very careful with that. So it's minus a negative here. I don't like the method of joints because one little mistake will throw everything else off. So be very careful with that. And then sine theta, 15 over 17. I'm using this angle. Sine opposite over hypotenuse. Okay, I blew it here. I ran out of space. So this is all equal to 0. Okay, so it looks like I have two unknowns here, F sub BC and F sub BH, but I can still clean this up, so that's what I'm going to do. I'll write this in a clean and hygienic fashion. Okay, so cleaning it up, I get this equation. Verify my arithmetic. Well, one equation and two unknowns, so I need a second equation. Well, why don't I find the sum of the forces in the y direction? That'll give me the second equation that I need. Okay, so put this off to the side, and now I'm going to create another equation. So the sum of the forces in the y direction is 0. Do you know where I'm getting these? Negative 300. It's this load, minus FBA cosine theta. That is the vertical component of F sub BA. minus f sub bi. Okay, well, I crossed it off and I put a 0 there. I determined that was a 0 member previously. Minus f sub bh sine beta. So that looks like it is the vertical component of this vector. Plus f sub bc sine alpha. So that's the vertical component of this vector. Okay, so the f sub ba, I know that. The cosine theta, I know that. F sub bi, I kiss that goodbye. Minus f sub bh sine beta. Sine opposite over hypotenuse. So 2 over 4.25. F sub bc sine alpha. Opposite over hypotenuse for alpha. Sine of alpha. Okay, so cleaning all this up, I get equation 2. So 2 equations and 2 unknowns. So now I'm going to solve these 2 equations for f sub bc and f sub bh. And solving those 2 equations, I get f sub bc 524.16, the 6 repeats, pounds in compression. F sub bh 318.75 pounds in compression. Okay, so now I'm going to go back to my original drawing and check these off. If I had a bigger drawing, I could write the numbers directly on the figure. But this is a pretty small drawing, so I'm not going to try to squeeze in too much information. So f sub bh, I got that. And I got f sub bc. bc, where is that? Right here. Okay, so what joint should I analyze next? Can I analyze C? Well, I'd have 3 unknowns there. Unknown, unknown, unknown. What about joint H? Okay, joint H. 1, 2, 3, 4. I've got 4 bars feeding into joint H, but 2 of the member forces, 2 of the bar forces are already known, meaning that there's 2 unknowns, F sub HC and F sub HG. So I will analyze joint H next. And now here's joint H. Joint H right here, I've got F sub HI pointing off to the left. Joint H is in tension, 943.75 pounds. F sub HG, I'm assuming that bar HG is in tension, so I show the arrow pointing off to the right. F sub HC going up. F sub HB at an angle of beta with a horizontal. I determined F sub HB the same as F sub BH. And I determined F sub HI, which is the same as F sub IH. Okay, so this is joint H that we're talking about now. Okay, so I notice that if I take the sum of the forces in the x direction, I can solve this for F sub HG, so that's what I'm going to do, take the sum of the forces in the x direction. And like magic, it gets done. So the sum of the forces in the x direction is 0. F sub HB cosine beta, it's the horizontal component of this vector, minus F sub HI pointing off to the left, plus F sub HG pointing off to the right is equal to 0. F sub HB, that was determined to be in compression, so be careful of that double negative there. Cosine beta, where am I getting that? Remember this? Cosine beta, 3.75 over 4.25. Minus F sub HI, I determined that previously. I find that F sub HG is 662.5 pounds. So now take the sum of the forces in the y direction to find F sub HC. And there it is. So the sum of the forces in the y direction is 0. F sub HB sine beta, the vertical component of this vector, plus F sub HC, that vector is purely vertical. So doing the arithmetic, F sub HC 150 pounds in tension. So let me go back to my original drawing. What did I just find? F sub HG, that was the 662.5 pounds in tension. And F sub HC, 150 pounds in tension. So now I got that. So what joint should I analyze next? Can I work on C? So at joint C, I'll have 2 unknown bar forces, or 2 unknown member forces. So I think I'll work on joint C next. So did I do this correctly for joint C? How does this look? So I've got 2 unknowns here, F sub CD, F sub CG. I'll find the sum of the forces in the x direction. I'll find the sum of the forces in the y direction. Pay close attention to the theta, the gamma, and the alpha. Make sure you know how I'm getting those. So how does that look? Sum of the forces in the x direction, 0. So 200, that's this one. 200 to the right. F sub CD cosine alpha, the horizontal component of this vector. F sub CG cosine gamma, that's the vertical component of this vector. Pardon me, the horizontal component of this vector. Minus F sub CB sine theta, that would be the horizontal component of this vector. So taking the sum of the forces in the x direction, okay, I have this messy looking equation. Okay, you know where I'm getting all the cosine alpha, cosine gamma from? Remember that illustration with all the special triangles? Remember this? Okay, so putting all this together, I wind up with what I call equation 3. One equation and two unknowns. The two unknowns, F sub CD and F sub CG. So I need to find the sum of the forces in the y direction to give me the second equation. So I set up an equation for the sum of the forces in the y direction, negative 300. That's this load on the joint, plus F sub CD sine alpha, the vertical component of this vector, minus F sub CG sine gamma, the vertical component of this vector, minus F sub CH, that's this vector going down, minus negative 524.16 times 8/17. So that's the vertical component of this vector. Watch that double negative in there, you do need that. Okay, so I clean it up there at the bottom, and then going on to the next sheet, I wind up with this equation. So two equations and two unknowns, equation 3 and equation 4. So I'm going to solve those simultaneously to find the F sub CD and the F sub CG. Now solving two equations simultaneously, I get F sub CD is negative 356.527 pounds, F sub CG about negative 508.69 pounds. Or I can list it like this. Maybe I'm a little sloppy with the notation. If I list it as being compression, I don't show the negative sign in front of it. If I just put a negative sign in front of the number without explanation, then we take it for granted that it's compression. But I can remove the negative sign as long as I state that it's in compression. Maybe I was sloppy with my notation previously. Okay, so I got CD. Got that one. And I got CG. That's this one. Okay, what should I analyze next? Can I analyze joint D? At joint D, I've got 3 unknown bar forces. That's too many. At G, I only have 2, so why don't I analyze joint G next? And now I analyze joint G. Does it look as though I transferred all the information over correctly? How do you like that? I used the exact answer for the bar force in member CG. Okay, so I want to find F sub GD and F sub GF. So I'm going to find the sum of the forces in the x direction, find the sum of the forces in the y direction. I'll do the y direction first. So I find F sub GD, the sum of the forces in the y direction is 0. So I've got F sub GC sine gamma, the vertical component of this vector, plus F sub GD, that's purely vertical. Okay, stick the appropriate numbers in here. This part is the F sub GC part. This is a sine of gamma. I remember those special triangles I drew earlier. That leaves F sub GD as the only unknown. So I'm getting F sub GD 371.1 with a 1 repeat. And now I'm going to find the sum of the forces in the x direction. So finding the sum of the forces in the x direction, negative FGH, that's this bar force, minus FGC cosine gamma, the horizontal component of this vector, plus FGF, that's the force in member GF, is equal to 0. I stick in all the appropriate numbers. F sub GC, be careful, you need the double negative here. And then cosine gamma, that's one of the special triangles that I designated earlier in the video. And then F sub GF is the unknown. I back it out. F sub GF is 314.58 pounds approximately. That's in tension. So now I've found the member force in GH, not GH, I mean GD and GF. Well, I did find GH earlier, but for this particular calculation, I'm finding GD and GF. Okay, so back to this. GD, that's this bar, and then GF is this bar. Okay, so what do I analyze next? Can I analyze joint D? Do I have enough information to analyze joint D? Two unknowns, so why don't I analyze joint D? And now here's joint D. Joint D, here's the original drawing. So I've got joint D here. DC, I know there's a 300-pound load acting down. I know DG. Do I have all those in place? DE and DF are the unknowns. Okay, and notice the angles that I have here, theta, delta, and alpha. So I propose finding the sum of the forces in the x direction. So how is this? Sum of the forces in the x direction is 0. Negative FDC sine theta, that's horizontal component of that bar force, plus FDE cosine alpha, horizontal component of this bar force, plus FDF cosine delta, so that's the horizontal component of this bar force. Okay, so the FDC I already know, put that in there. Sine theta, remember this? Sine theta, 15/17. Plus FDE. FDE, I don't know that, do I? Cosine alpha. Okay, alpha, where is that? Alpha, that's 15/17. Okay, so plus FDF, I don't know that either. Cosine delta. Okay, so remember this triangle? This one, cosine delta, adjacent over hypotenuse, 3.75 divided by 1/4 square root of 801. So that's where I'm getting this from. Okay, so now clean all this up. I'll have a equation with two unknowns. So I have equation 5. I clean everything up and I have an equation that I call 5. I don't think I've used 5 yet. Okay, so now find the sum of the forces in the y direction and set that equal to 0. Take a good look at this, because the next equation that pops up will be the sum of the forces in the y direction, and I'm going to set that equal to 0. Now the sum of the forces in the y direction is 0. Okay, you see what I have here? You know where I'm getting all these from? Okay, so minus 300 plus FDE sine alpha, it's the vertical component of this vector, minus FDF sine delta, vertical component of this vector, minus FDG, that's this vector, minus FDC cosine theta, vertical component of this vector. A lot of this stuff I already know. The FDE I don't know. The FDF I don't know. Everything else I stick in the appropriate values, and then I continue on the next page. So I have equation 6. So the unknowns are F sub DE and F sub DF. Those are also the unknowns for equation 5. So now I'm going to combine equations 5 and 6. Equations 5 and 6, I'm going to use those. I'm going to solve those simultaneously for F sub DE and F sub DF. Solving them simultaneously, I get F sub DE is 0 pounds, F sub DF, negative 755 times the square root of 801 divided by 36. I forgot to write it, but that's approximately 594 pounds in compression. And I forgot to put compression there. Okay, so FDE is 0. That seems weird. Okay, so go back to the original drawing. FDE is 0. Here, I'll just put a 0 here. 0. And then FDF, got that. So FDF, I got this bar. Okay, so it looks as though EF is the only bar force that's still unknown. That seems weird that the bar force in DE is 0. Could I have figured that out by inspection? If I had analyzed joint E, you notice that there are no external loads on joint E. So by inspection, I could have told you that the bar force in DE is 0. What about bar EF? Do you think there's any force in that? Well, if you analyze joint E, there's no external load on joint E, so I predict that the bar force in EF is also 0. So both DE and EF are 0 bars. Well, why don't I check joint F just to verify all that? So I'm tentatively going to predict that bar EF has a bar force of 0, and I'm going to analyze joint F. At F, I've got the vertical reaction, I've got bar force FG or GF, I've got DF or FD. I'm going to try to figure out FE now, based on analyzing joint F. So here's joint F. I want to verify that the sum of the forces in the x direction is 0. Okay, so I found F sub DF previously, I found F sub GF previously. So it looks like there are no unknowns in the x direction, but I want to verify my values anyway. So the magic happens. Okay, negative F sub FD cosine delta minus F sub FG, perhaps equal to 0. I put a question mark there. Okay, the next line, let me bring a ruler in here. Okay, so is this true? So I stick in the appropriate numbers. Okay, I put a question mark here. I haven't verified that it's equal to 0 yet. Okay, and then take it down to the next line. Okay, so this part becomes the 314.583, where the 3 repeats. This number is this number. So obviously, the left-hand side of the equation is 0. The right-hand side is 0. So I say, aha. It's verified in the x direction that this joint F is in equilibrium. So now I want to find the sum of the forces in the y direction to find F sub Fe. So I sum the forces in the y direction. F sub Fe plus F sub Fd sine delta, the vertical component of this vector, plus F sub y, that's the reaction at F, should be equal to 0. Stick in all the appropriate numbers. F sub Fe is the unknown, so I arrive at this equation. F sub Fe, this mess in parentheses, hang on a minute, this mess between the pens here, that becomes negative 503 1/3. And then the 503 1/3, that's this one here. Okay, so as a former professor of mine always used to say, as any fool can plainly see, those two zero out. So I arrive at the conclusion that F sub Fe is equal to 0. Okay, so 0, bar Fe is a 0 force member, or a 0 bar. F sub Fe is 0. Isn't that what I said it would be a few moments ago? So let me bring back my original drawing. Okay, so now I found F sub Fe to be 0. So by analyzing the joint F, particularly in the y direction, I was able to find F sub Fe is equal to 0. But I could have done that by inspection, by looking at joint E. By looking at joint E, there's no external forces acting on E. Therefore, bar ED and bar EF must both be 0 force members, or 0 bars. So that kind of brings it all together. That demonstrates that my calculations must be true. The fact that everything seems to come together just fine. Everything comes together correctly. So if I have a 0 bar, does that mean that I can just take it out? Can I just remove DE and FE if those are 0 force members? Can I take those out? Technically yes, but this is a textbook style problem where we've got loads acting at specific locations, or point loads. In reality, things happen, like loads shift around, or maybe another load might suddenly be introduced. So 0 bars are not completely useless. They do account for load shifts and just add to the general stability of the truss. So I'm happy with having those bars there in this mono truss. So now you could put together a table that summarizes all this. It lists all the bars and the forces in each bar and whether they're in tension or compression.